Good evening, one and all present over here. So my name is Arpit Desai from MTech VLSI Design Branch, and today I'm going to present a paper on fast bring up of an SoC of an artificial intelligence SoC through IEEE 1687 protocol, integrating embedded TAPs and IEEE 1500 protocol interfaces. So we're going to talk about the complex application specific system on chips which are being developed for hardware support and also involving artificial intelligence applications such as like complex SoCs which are integrating on a chip overall. As a concept, if we talk about on chip and off chip memories, there are tremendous amount of cores and interfaces which are being in a hierarchical base for the embedded TAPs. So we are going to talk about the security measures as well as the DFT structures for these particular cases. Uh, the IEEE standards which are involved are 1687 to 2014 IJ tags, which are also used to integrate a different components into a single unifying methodologies. So coming to the extract part, specific to the complex applications, hardware support for artificial intelligence applications is being developed by using the system on chips. So basically, artificial intelligence applications are being used in such a way that the hardware support for these SoCs is being, uh, it's becoming complex day by day. So, how these AI hardware accelerators are becoming more and more popular. Like the main computing power engines of these applications holds the main core purpose of these particular designs. So, as even the data is being significantly improved day by day, and a lot of data is being come into the picture. Also, the AI performing these applications require a very strong base for hardware architectures as well. So this paper is basically focusing on the hardware part of it. So as a VLSI engineer, we also look into the part of security measures as well as the DFT structures, and also involving the standard IEEE patterns for these applications as well. We have the advantages of workflow efficiencies and quick silicon bring ups as a result for this. And for example, we can also say that silicon bring up of the DFT of the entire SoC took around 4 days, and that of the other part of SoCs took even less time. We can also say that it took around 8 days as per this particular paper has been considered. Moving forward for the some of the FAQs which are involved when I went through these papers, I some of the frequently asked questions which I found on Google were like, what makes an artificial intelligence SoC? So this was one of the frequently asked questions. And what makes it an AI SoC? What are the deep learning SoC challenges? And what are the leading AI processor options? So as we are going to talk about the hardware accelerators, we also need to focus on some of the processor options. Before going into the algorithms, we just thought about going through some of the basics. So what is an AI SoC? So the growth of artificial intelligence demands that the semiconductor companies re-architect their entire system on chip designs to provide more scalable levels of performance, flexibility, efficiency, and integration. So basically, and artificial intelligence is kind of a like it mimics a human behavior. So machine learning basically uses advanced statistical models and different kind of complex algorithms to find patterns as well as the results. So uh, there are also some kind of an algorithm which comes to the picture, basically probability which are being involved. So Bayes theorem, decision trees, neural networks, clustering, uh, vector machines, deep learning, which comes into the picture. And when these all applications which are being involved on a chip, the chip, the hardware of this chip should be able to handle these kind of handle these kind of activities. Also, when even convolutional neural network comes into picture, the recurrent neural network, spiking, as well as capsule when they come into the picture, these all involving in a particular application specific system on chips makes it an AI SoC. Some of the key factors are the accuracy and the timelineliness of the incoming data, the reliability and efficiency of AI models results in resulting algorithm, speed and efficiency of the underlying system hardware, including for sensors, controls, and even for actuators as well. So, what makes it an AI SoC? Uh, like, I mean to say, like the vast majority of interferences in in the signal and the communication domain as well, a vast majority of training activities which are happening, because suppose as I told, it also mimics the human behavior. So the more and more training and the more and more data which it has to store in, that also plays like it makes it an AI SoC. It's also enabled for better than human error capabilities as well. So even the vast majority of investments for AI SoC is power per performance activities which are also being involved. And most of the time the communication neural network or the RNN or some of the SNN solutions which involved some of the software development kits for mapping AI graphics to hardware are being most competitive, including the neural network hardware accelerator here as well. So deep learning, uh, like what are the deep learning SoC challenges? So basically, it involves unique requirement for processing. So basically, the most of the processors which are going to talk about, it requires a particular application based specific requirements only for the processing part. Also memories which are being involved, like the more the memory, like the RAM which is being involved, if there is a more RAM, so more RAM includes more number of CPUs, and more number of CPUs means more number of cores. So the processing of this particular of a particular AI SoC smoothens the entire process. So uh, the sole purpose of whatever this paper meets the criteria. Connectivity also plays a very important role, because uh, even the power planning, how power is being involved in these GPUs or the hardware accelerators plays a very important role, as well as security concerns. So some these are the leading AI processors, and the ASIP designer is another one of the leading processors in the AI domain. Design application specific instruction set processors, unlimited design flexibility. So these are one of the specifications of these processors. So there are many other uh, processors as well, which is again embedded vision processor IP is there, and there is CNN engine, AXI interconnect. Uh, there are MAC engines, as well as uh, like DSP, like ARC HS47 is one of the DSP architectures for controls and scalability DSPs, and also ARM processors also being involved in a very generic way actually. So moving forward, so this is an Enflame design. So basically, an Enflame design is such a, it's like a general test methodology aspects part, wherein it incorporates an ASIC die with the multiple stacked high bandwidth memories. So also it involves a lot of DRAMs, which dies like DRAM dies on a 2.5D interposer. So like this particular ASIC die is involved with a lot of stacks. So there's a IGT, ITAG, and there's a PTAPs, controllers, and there are a lot of metal layers has been involved. So here this ASIC die includes many DSP based core as well. So DMA cores, there are SRAM memories, and the DFT of the ASIC die was mainly being used for this particular AI architecture. So it involves DRAM dies, and this is also an interposer die as well. So IJ tag as an integrating methodology is used to like in the top level test patterns, such as for multi-IP applications. It is involved in such a way that every particular course and these DRAMs and these dies are being integrated properly for the end flame design. So going forward, sorry. So this is a tap access infrastructure. So tap access infrastructure involves like it involves one of the CDFT CDFT core part, wherein it has a lot of pad OBS like debug input outputs. So the IJ tag pads involved logic are being sent to the descent tap using the JTAG signals, and